Good morning friends, and welcome to the next lecture of this video course on advanced hydrology. In the last class, we looked at an example of how to calculate phi index given the rainfall data and the runoff data. Then we also looked at the concept of a W index and the runoff coefficient. Okay. These are all the methods of accounting for abstractions from precipitation while we are doing some kind of rainfall runoff modeling. Then we moved on and started developing an algorithm for abstractions from precipitation due to infiltration, that is, and then we said that we will develop this algorithm using the Green-Empt equations. We defined the problem, we looked at what are the data given, what do we need, and what are the outputs from this algorithm. In the process, we defined three ponding cases, all right, case 1, case 2 and case 3, in which we said that while we develop this algorithm for abstraction from precipitation due to infiltration, we march in time domain, that is, we analyze each time step or each time interval, and while we do that, we can encounter three possible cases. All right. So, all the time intervals will fall either of these in either of these three possible cases, and we had said that the case 1 is ponding throughout, case 2 was no ponding throughout, and the case 3 was when the ponding starts somewhere in between in that particular interval. Okay. That is where I think we stopped, and then what we will do today is we will start or we will look at the flow chart, all right, or the algorithm, how it can be developed. All right. As I said, we will just look at the flow chart, and then the coding can be done or a computer program can be written looking at that flow chart. Okay. There is a solved example given in the book, in the Venti-Chow's book, on this particular flow chart or this algorithm. I will highly encourage that all of you write your own code, all right, a small little computer program in which the rainfall data would be given, the Green-Empt infiltration equation parameters will be given, and then what you would have to find out is effective rainfall heatograph. All right. So, that will be a very important component in a rainfall runoff model. Okay. So, let us get started today by looking at how we will find the infiltration, all right, by analyzing every time step. So, the first step would be we will compare infiltration at time t with I, or I is the rainfall at time t. Okay. So, you have this. This will involve either of the two cases. Okay. So, either you have infiltration less than or equal to I t, or it is greater than the rainfall intensity. Okay. In the first case, which case is this? All right. In this case, when you have the intensity of rainfall is higher, okay, throughout, then you would have what is called the ponding case 1 or ponding throughout. Okay. Then what we do is we use the associated equations, which would be f at t plus delta t minus f at t minus psi delta theta natural log of your f t plus delta t plus psi delta theta, all right, divided by f at t plus psi delta theta. Okay, you close this bracket, it should be equal to, on the right hand side you would have equal to k t. Okay. So, this is basically your equation number 5.4.2. Okay. So, we do what we do is we analyze the f t with I t and then compare and then see which case it is. So, if that is true, this will be case 1. Okay. You come here on the other side, you would have What is this now? The rainfall intensity is less than the infiltration intensity or infiltration rate at time t, all right. So, this would be either case 2 depending upon the 3 ponding cases we had seen yesterday, you can see that easily, or it will be case 3, all right. It could be either of these 2 cases, all right. Now, what we do is in order to distinguish between case 2 and case 3 is we calculate the rate of infiltration at the end of the time interval, all right. We calculate the variables at the end of the time interval and then we compare that with the infiltration the rainfall intensity. The rate of infiltration at the end of the time interval we compare with the rainfall intensity, and that will tell us whether it is case 2 or case 3 depending upon where the relative magnitude is. Okay. So, what we do is we calculate, and because these are intermediate variables we will denote them as prime. So, let us say you find out f prime at t plus delta t as f at time t, which is supposed to be known, plus rainfall intensity times delta t. Okay. And this is equation I am taking 5.4.3 basically from the book. And once we know capital F prime, you can always find out small f prime, okay, from the Green-Amt equation. So, this would be nothing but equal to k times psi delta theta over capital F prime of your t plus delta t, all right, which we have just found out, plus 1. This is the basic equation of the Green-Amt. So, we have the rate of infiltration at the end of the time interval. Now, we compare this with the rainfall intensity at the end of the time interval, which is same as I t, because we said during an interval rainfall intensity is constant. Okay. All right. So, the next step then is we compare f prime t plus delta t with I t. I am writing I t, but you understand that I t and I t plus delta t are same. Okay. Okay. Then if your f prime t plus delta t is less than I t, we go in this direction, okay, and if not, then we go in this direction. Let us say f prime t plus delta t, that was less, and this is greater than equal to I t. Okay. Now, let us look at this case first. Which case this would be? Can anybody tell me that? When the rate of rainfall is less than the rate of infiltration, all right. Obviously, it is a case of no ponding, whether there will be ponding or not, there will be no ponding actually in this case, all right. So, at the beginning there was no ponding, at the end of the time interval there is no ponding. So, you have no ponding throughout, and that is case 2. Okay. So, this way we are able to distinguish, and then we can say that this is your case 2 of no ponding. Okay. And then we use the appropriate equations, and all we say is that f at the end of the time interval is nothing but whatever we had calculated f prime and t plus delta t, and similarly your f at t plus delta t is equal to f prime, which we had calculated, your t plus delta t, okay, which we have calculated already. So, this is your case 2, and then what is the case 3? This is obviously your case 3, all right, the last one, in which you have the ponding partways, where the ponding starts somewhere in between. Okay. So, what we are going to do is I will write the set of equations, all right. What we need to do in case 3 is we need to determine the time, exact time when the ponding starts within that time interval delta t, all right. So, let us say your delta t is 1 hour, all right, and you are into the 5th hour. So, during from 4th hour to 5th hour, exactly when the ponding starts, that is what we want to find out, and we will call that a variable called delta t prime. And once we find the delta t prime, then we can calculate the infiltration. Everything before that is your whatever rainfall falls, after that we use the green empty equations. All right. Okay, so the corresponding equations then would be your f of t is equal to I t, f capital T would be f, let us say at p, then we calculate f p using the equation we have k psi delta theta over I minus k, I at t, that is. This I am using 544, right. You can look at these equations, and then once we have that, we can find out delta t prime from our ponding time equations, and that would come out to be f p minus f t, which we have just found, divided by I t. Okay. And then exact time to ponding would be your t at the beginning of that time interval plus your delta t prime, which you have just found out. Okay. So, this way we can find out what is the exact time to ponding for the case 3, in which the ponding starts somewhere in between in that particular time interval. Okay. Now, I need to close down this loop. So, you have a tree coming up, coming down, and then all of this algorithm has to converge somewhere, right. So, let me see, from the case 1, let me say that I am going to have a box here, in which I am going to set t is equal to t plus delta t. All right. We have analyzed the first or tth time step or any time step, and then I increment that. All right. So, this is going here, the logic will flow from here, from case 2 to here, and then from case 3 also it will flow there. Okay. So, once we have analyzed the time interval delta t, all we do is we increment the time step, that is we start looking at the next time step. All right. And then we apply or test for the condition is your t or the time last one. All right. If the answer is yes, you say you are going to stop. Okay. If it is no, then what do you do? Well, you go back to your origin, all right, and then start analyzing the whole thing over and over again. Okay. So, this way you see that the logic would flow, that you will start with the first time step, analyze whether it is case 1 or case 2 or case 3. All right. Depending upon that, we calculate the rate of infiltration and cumulative infiltration at the end of the time interval. Okay. Once we have done that, we can find out the incremental infiltration at each time step. All right. Once we have that, we can subtract the infiltration from the rainfall, all right, or the rainfall heatograph, and develop what is called the effective rainfall. Okay. So, if I did that, let me just try to demonstrate that. If this was your let us say this is your rainfall heatograph data. Okay, in which this is your time and this is your what I, rainfall intensity. Okay. Now, as a result of this algorithm which we have developed, we have calculated the rate of infiltration or the actual infiltration as a function of time. Okay. So, let us say it was this, something like this. Okay. So, everything above that is your ERH. Okay. What does this represent? This is your ERH. Does this contribute anything to ERH? No. Why? Because this is which case? This is the case of no ponding throughout, right. So, this is not towards your ERH. Okay. So, you see that we have looked at this algorithm in which we have the rainfall heatograph, and we can convert that into effective rainfall heatograph by subtracting losses due to infiltration using Green-Empty equations. Okay. The algorithm which we have developed does not account for the initial abstractions, we had said that earlier. However, if we have the initial abstractions estimated somehow, they can be incorporated before infiltration can be subtracted. Okay. So, that way we have done half of the rainfall runoff modeling as far as calculation of the losses is concerned and calculating the effective rainfall is concerned. And then we can go either to the unit hydrograph or any other complicated rainfall runoff model, but we will not start that yet. Okay. So, this is the algorithm, and the next topic we will start in this chapter is we will look at some another method which is also very important and very simple to use. All right. This algorithm of course is slightly complicated. One has to understand the process of infiltration, ponding cases, analyze everything and then develop this program. Okay. In practice there are some very simple methods, all right, and one of them is what is called the SCS curve number method, and that is what we are going to look at next. SCS method of abstractions. This method is based on a certain concept or assumption. Okay. We would look at that first. What it says is that the actual retention in a catchment divided by the potential retention. Now, what we are talking of the retention of the water storage, okay, is linearly related with the actual runoff over potential runoff. Okay. Before I actually go into the details, I must mention that this SCS curve number method or the SCS method was developed by, what is SCS? SCS is an organization in the United States. It is called Soil Conservation Service. All right. So, what is SCS? It is the Soil Conservation Service. It is an organization, water resources organization in USA. Okay. They have developed this method, and this method is applicable for storm rainfall only. What do we mean by that? That this is applicable to an isolated storm. All right. This is not meant to be finding the effective rainfall or the direct runoff hydrograph on a continuous basis. All right. This is only for the maybe the flood events or the isolated storm events. Okay. It is not for the continuous modeling. All right. So, we will look at this concept. Before we understand this, I think we would need to define certain physical variables that are involved in this equation or this method. So, let us look at them first. So, first let us look at them graphically and then we will come to the equations. Okay. This is what we are looking at is the, let us say, rainfall heatograph. Okay. And then there is some form of, this is your losses. So, everything above will contribute to the DRH, okay, and everything below is what is called the losses. All right. However, let me first say that this is time and this is your I or losses, and let us say that this is your IA, this is your FA, and what we are seeing on the top is PE. All right. And total P is your PE plus IA plus FA. Okay. So, the total rainfall is P. It is divided into three components. Where does all the water go? All the rainfall that falls on a catchment gets converted into three parts, or this gets distributed into three components. All right. One is the effective rainfall, one is the initial abstractions, and other is the FA. Okay. All right. So, let me just define all these parameters then. First, P is the total depth of precipitation or rainfall when during a storm event. Okay. Remember, in the SCS method we are talking about a storm event. All right. So, during the whole storm, it may be 3 hours, it may be 10 hours, it may be 24 hours. So, during that whole duration, P is the total depth of the rainfall or the precipitation. Okay. I A is the initial abstraction. So, you see that this method does account for the initial abstraction before ponding. Okay. PE is the excess precipitation or effective rainfall, commonly known as or direct runoff. What is excess rainfall or effective precipitation or excess precipitation? That actually runs off, because all the requirements of the storage in the catchment below the ground have been satisfied. All right, all of those retention has been satisfied. So, everything else will run off as effective rainfall. Okay. FA is your depth of water retained in the catchment or in the watershed. And let us define one more parameter which is not shown on that figure on your right. We will say capital S is the potential maximum, all right, potential or maximum what? Retention in the catchment. Okay. So, what we are saying is that capital S is the maximum possible or the potential retention of the catchment, how much water a catchment can store. Okay. This is the maximum. All right. However, during any given rainfall at any given time, all right, it would be less than that, right. So, that we are defining as F subscript A. F A is the actual retention. Okay. Now, with this terminology, let us come back to this equation or the assumption or the concept or the basis of this SCS method, in which what we have said is that the ratio of the actual retention to the potential retention is equal to the what? Actual runoff to the potential runoff, the ratio of the actual runoff to the potential runoff. All right. So, let us look at these quantities. What is the actual retention? We have just said is F A, okay, the way we have defined all the parameters, divided by the potential retention, which is capital S. Okay. This is equal to, we are saying, actual runoff over the potential runoff. What is the actual runoff? The excess rainfall, that will become your actual runoff, direct runoff. Okay. Divided by what is the total or the maximum possible runoff? Well, it is the rainfall, and what part of the rainfall does not become runoff? Well, it is only the initial abstraction. Initial abstraction does not contribute anything to the runoff. Okay. So, this is the equation basically then or the concept on which this method is based. So, let me number this equation as 5.5.1. The other equation is, as we have already written, the total P is sum of these three components, that is P E, the excess rainfall plus abstractions plus the actual storage. All right, and I call that 552. Okay. Now, what we will do is we combine these two equations. Okay. The mathematical or the algebraic manipulation we will not go through. Should be easy to see that once we combine these two equations, we can find the following relationship, which is P E is equal to P minus I A whole square divided by P minus I A plus S, and let us number this as 553. Okay. Which is the basic equation for computing the depth of excess rainfall, or ER I will say in short, or the DRH or the direct runoff hydrograph from a storm by the SCS method. This is the basic equation. Okay. Now, there is one quantity IA, or the initial abstraction. So, what SCS has done is it has given certain guideline to estimate IA in the absence of any other method. All right. You are expected to calculate or estimate this initial abstraction separately depending upon the catchment characteristics in that particular catchment in which you are applying this equation. However, if there is no information available, they have said that based on certain experiments which they conducted on small catchments. All right. Again, this is not going to be applicable to the large catchments. So, for the small catchments, the SCS has found that your initial abstraction is about 20% of your maximum retention S. Okay. So, 0.2 S, if it is 5.5.4, we put this back into 5.5.3, and the final equation then would come out to be this. This is 0.8 S in the denominator. That is your final equation. Okay. So, this way we see that if we want to find out the axis rainfall from a storm based on the SCS method, all we need to know on the right hand side of what? Well, of course, we need to know the total precipitation, capital P, the data that will be known to us. There is a parameter called capital S, or the maximum possible retention. All right. The SCS has tried to characterize or quantify this parameter S for a catchment depending upon the catchment conditions. All right. It will depend upon what? This is basically representing the storage in the catchment, right. So, on what things the storage will depend? Well, it will depend upon the soil type, the land use condition, the infiltration, and the storage characteristics and so on. Okay. So, what they have done is they have characterized this in another parameter called a curve number. Okay. That is why this method is also known as SCS curve number method. Okay. So, the next thing we will look at is the curve number concept. Or CN. Okay, is a parameter representing retention of the catchment, that is S, right. It is another parameter, as I said. In other words, actually it is also quantifying the perviousness, how pervious the parameter is. Okay. Okay, and the relationship is that S is given as 1000 over the curve number minus 10. Okay. And this is, let us say, 556. Then obviously, I think I forgot to number this. This is 555. Okay. Okay, where this Cn is what? It is a dimensionless number. It does not have any dimensions. Dimensionless number, and its value is ranges between 0 to 100. Okay. Let me go with curve number is equal to 100 means completely impervious catchment. And if the curve number is 0 means completely pervious, which actually does not occur in real life. Pervious, completely pervious catchment. Okay. And normally the curve number would be between 0 to 100. Okay. So, when the curve number is close to 100, we are saying the catchment is completely impervious. Impervious means what? There is hardly any infiltration. All right. It does not allow the water to infiltrate. All right. So, what kind of a catchment would that be? in which there are lots of buildings, there are lots of roads, there is lot of parking areas, lot of streets, right. So, all of those areas will not allow the water to infiltrate. Okay. So, if you have any highly industrialized catchment, in that the curve number will be high, right, and accordingly the storage characteristics would be different. Okay. If you have a rural catchment in which there is lot of grassy areas and vegetal cover, that will allow higher amount of infiltration. Okay. So, that will have the capital S or the storage value depending upon that curve number, because that is very small. Okay. So, this way the curve number is defined, and then next thing we look at is what is called the antecedent moisture condition. Okay. Before I actually go to that, I must mention that this curve number has been defined, or these have been calibrated or given by the Soil Conservation Service depending upon the soil type and the land use pattern. All right. The SCS has classified all kinds of soils into 4 kinds, class A, class B, class C and class D. All right. So, depending upon whether you have clay soil or the sandy soil or the loam or whatever, you first find out whether it classifies into A or B or C or D. Okay. Once you have done that, then you look at the catchment conditions, all right, whether it is the residential, whether it is rural, whether it is paved areas or different kinds. All right. Within rural and within urban areas, there are various categories. All right. So, depending upon these 2 parameters, the curve numbers have been specified. All right. And in the book there is a table, all right, which specifies the curve number as a function of these 2 things, as I said, which is the soil type and the land use, land cover conditions. Okay. In short, that is what I am writing. So, what you can do is, depending upon what type of soil is there, what type of LULC conditions are there, you just read off from the table, you can just pick up the value of the curve number for the catchment. Okay. Again, I should point out that in a large catchment, you can expect lot of heterogeneity. That is, there can be more than one type of soil, there can be more than one type of land use, land cover conditions. So, in that case, it is possible to classify your whole catchment into small sub areas, then you assign a curve number depending upon the soil type and the land use, land cover conditions, and then you can compose it, or you can find out a weighted average of the curve number. Okay. So, actually I did not want to go through that step yet, but it is possible to model or characterize a composite or a complex catchment also using the SCS curve number method. Okay. So, these are the 2 things, and then another important thing when we are doing this rainfall runoff modeling or the calculating the direct runoff hydrograph is the initial conditions. Okay. Let us say you have the same rainfall event or you have a catchment, you have 2 different rainfall events of the equal magnitude occurring with the same distribution. All right. However, the initial conditions were different. Okay. So, if you use the SCS curve number method, all right, it will give you the same curve number, because the curve number depends on what? As of now we have said on the soil type and the land use, land cover conditions, which are going to be same, right. So, it will give you the same amount of excess rainfall depending upon different initial conditions. All right. So, we have to account for the initial conditions or the what is called the antecedent moisture conditions. Okay. So, what they have done, the SCS people, is that they have defined the curve number for what is called the AMC condition 2, which is the normal condition. Okay. And then they have given certain equations using which we can convert the curve number for different initial conditions. Okay. So, what they do is the AMC conditions or the antecedent conditions are defined into 3 classes or 3 types: AMC 1, AMC 2 and AMC 3. Okay. One is, let us say, your dry, second one is normal, and the third one is the wet. Okay. Instead of the direct magnitude, what they are doing is they are just classifying the initial conditions into 3 types, all right, dry, normal and wet. The curve numbers that are given in the table are for normal, all right, and then we have equations which will convert the curve number for the drier conditions and the wetter conditions. And how we define or how we characterize these 3 different AMCs? Well, what they do is they take the antecedent rainfall for last 5 days. Okay. You look at the rainfall for the last or the previous 5 days, the total rainfall, the cumulative rainfall, all right. Depending upon the magnitude of that cumulative rainfall for last 5 days, you say that the current conditions are either dry or normal or wet. Okay. This rainfall for the last 5 days also they have defined for the dormant season and for the growing season for the benefit of the rural areas or the agricultural areas, all right. So, for the dry I will just throw these numbers at you, it is 0.5, 0.5 to 1.1 and then it is more than 1.1. Okay. So, in the dormant season, if the last 5 days rainfall is less than 0.5, then you have dry conditions, all right. If it is between this, then you have normal, and if it is more than 1.1, then it is wet. And by the way, all these things are in inches. Okay. And in the growing season, this is less than 1.4 inches, this is 1.4 to 2.1 and this is greater than 2.1. Okay. So, we take the last 5 days rainfall data and then we find out what will be the current conditions or antecedent moisture condition, and then we look at the equations which can be applied. So, the curve number for the dry condition, that is AMC 1, is given as or given by this equation, which is 4.2 Cn for 2 divided by 10 minus 0.058 of your curve number for 2. Okay. As I said, the curve number which you will read off from the table is for normal condition, that is Cn 2. And then if you have the wet conditions, then you can convert or find the suitable value of curve number for the wet season as this, over 10 plus 0.13 of your curve number for the second conditions, this is 5.5.8. So, you can see that these are very simple equations to use. You just find out what is the curve number in your catchment. Okay. Using the curve number depending upon AMC 1 or 2 or 3, depending upon the soil type and the land use, land cover conditions. Once you have done that, you can convert that Cn into S, all right, and then you can use that S in your basic equation for the SCS method. So, you can get the effective rainfall. Okay. Now, I think we would move on, take a move on here, and the next thing we are quickly going to look at is what is called the urbanization effects in a catchment. Okay. What happens when a catchment goes through the process of urbanization over a long period of time? Okay. Let us say in 10 or 20 or 30 years, a catchment you will have you will see that there will be a lot of buildings coming up, there will be a lot of paved areas. So, the runoff from the catchment will tend to increase, the infiltrations would decrease, and the hydrograph characteristics will, or the runoff response from the catchment will keep on changing. So, what we want to just look at very briefly is what will be the impact of the urbanization on the shape and the magnitude of your runoff hydrograph. Okay. So, if you look here, let us say that this is your shape of the runoff hydrograph before urbanization or the before conditions. Okay. Now, during the urbanization process, what happens is the impervious areas increase. Okay. during the industrial due to the industrial activity or the economic development, you will have lot of impervious area coming up. So, the fraction impervious will increase. As a result, as you know, in the SCS method, what will happen? The curve number will increase. Okay. All right. So, what does that mean? That means that there will be less infiltration, right, and there will be more runoff. Okay. Also, what we say is the hydraulic efficiency. Hydraulic efficiency of the catchment increases. Okay. As a result of urbanization, we are saying the hydraulic efficiency of the catchment increases. Means what? Due to the lot of paved areas, all right, or the urbanization, all right, or the buildings coming up, you would have good drainage system also. Okay. Because the water will run off quickly, it will get collected into the small channels, into the bigger channels, and it will reach the outlet of the your catchment very efficiently, very quickly. So, the drainage system becomes more efficient. So, that is what we mean when we say the hydraulic efficiency of the catchment increases as a result of urbanization. Okay. What else? Well, that will result into increased and earlier peaks. Okay. So, as a result of the urbanization, we have seen that there will be less infiltration, more runoff, the peak will be higher, the peak will occur earlier. Okay. So, if this is my shape before the urbanization, on the same graph, before I do that, let me say that this is time and this is your runoff. Okay. That goes without saying. So, what you have then is something like this, okay, wherein this is your after urbanization. Okay. This difference you see this much. What is this? This is the increase in QP. Okay. All right. And then this time difference you see the peak. All right. What is this? This is the decrease in the time to peak. Okay. So, you see that as a result of urbanization, what happens to the runoff response from the catchment is that you have earlier peak and you have higher peak. Okay. So, after 10, 20, 30 years, you may have noticed that you have a catchment or your surrounding areas, in which if the rainfall used to occur 10 years ago, there will be no flooding. All right. The drainage system would be able to take care of the water. Okay. But because of the changing condition or the urbanization, that is no longer valid. Why? Because the drainage capacity of your drainage system has remained constant, all right, but the runoff generated, the peak discharge which are generated are more, for which the system is not designed. Okay. So, these concepts are important from the point of view of the drainage design basically. Okay. So, we will not spend too much of time on this, but we would move to a very important concept in this chapter, in which what we will do is we will look at the modeling of the surface water, all right, the overland flow modeling and the channel modeling. Until now we have looked at the modeling of the abstraction or the to the rain from the rainfall, how do we get to the effective rainfall. Once we have done that, then we want to find out how this effective rainfall gets converted into your direct runoff hydrograph, all right, or how the surface runoff and how the channel flow is getting modeled. All right. Okay. So, the next thing is your surface water modeling, and in which we would look at what is called the flow depth and velocity. Okay. What will be our objective? Okay. Our objective will be to find out the flow depth and velocity for the overland flow. Okay. So, what happens is at the rain falls, all right, on a catchment, okay, the infiltration takes place, that goes in, the remaining water or the excess rainfall starts to run off. All right, there is certain amount of holding capacity, the water starts to pond, but after some time that water starts to move because of the gravitational forces taking dominance. All right. So, the water or the surface water or the overland flow, it is also called the sheet flow. It starts to move very slowly initially, and then the velocities become higher, and then the water will start to move into very small channels, or these are called the rills. After some time, these channels will combine into bigger channels, and then bigger channels will finally get into the rivers and streams. Okay. So, this is the process of conversion of your effective rainfall to the flow in the rivers. Okay. So, let us look at it briefly, and then we will go to the mathematical modeling. So, you have initially the water ponding on the natural surfaces as the rain is falling. Okay. Then what happens is, this ponded water overcomes the surface tension forces, okay, or the surface retention forces, and begins to move. Okay. Initially, this overland flow moves as a sheet flow, very small sheet of water which is flowing slowly. Okay. For about 100 to 200 feet. Okay. This sheet flow will not continue for very long, all right, for about 100 to 200 feet. All right. After that, it will start forming the small channels. Okay. And after that, small channels start to appear, or small channels get formed. Okay. Then later, these small channels combine to produce recognizable channels. These small channels which we have just said, these are very small channels. It is actually if you look at it by naked eye, it will look like a sheet flow or the overland flow, but water is actually going through a very small channels. All right. And when many channels combine, many small channels combine, then we have what is called actually some recognizable channel flow. Okay. Recognizable channel flows. Okay. Okay. So, what we are then going to do is, we will model this sheet flow or the overland flow or the surface flow process, and what will we do? Again, we will go back to our basic principles or theorems which we have learnt in this course. Okay. Remember, in the beginning of this course, I had said we will develop a consistent mechanism for the movement of fluid, all kinds of fluids. All right. And we are dealing with water in the atmosphere, in the ground, on the surface, everywhere. Okay. So, we will be using your Reynolds transport theorem, your continuity equation in the continuity equation form and in the momentum form. All right. We will write the continuity and momentum, we will combine the two, and then finally, we will be able to write the expression for what is called the flow depth and velocity for the overland flow. Okay. So, let me say that we will be using the principles of, again, the continuity equation and the momentum equation to model this whole process. Okay. All right. So, let us then look at the overland flow modeling, and we want to find out the flow depth and velocity of the overland flow. Okay. So, what I would like to do is, I will just draw the schematic first, and then define various variables. We will define the control volume. Okay. All right. So, this is your direction x, this is your ground, okay, or this is your ground level. This angle is theta, this we call S naught, okay. Perpendicular to the x direction is, we say, is y, okay. This you are looking at the sheet flow, or the water is flowing from left to right, and what comes out is this, all right, which is your velocity v, and this is the depth of flow is, let us say, y, okay. So, you have a sheet flow or overland flow taking place from left to right, and at the outlet we have velocity is v and the depth of flow is y. That is what we want to actually find out in this particular case. And this dashed line which I have drawn is called the control volume. This is your, let us say, CV. What is happening is the rain is falling, let us say, I, at the rate of I into your control volume, okay. Infiltration is taking place into the ground, perpendicular to the ground, okay, which is, let us say, small f, and the length of the overland flow which we are considering, let us say, is L0, okay. So, let me then define all these parameters first, okay. So, you have theta as the angle between the ground, all right. The flow is taking place parallel to the ground, keep that in mind, all right. So, the theta is the angle between the ground and the horizontal, okay. You see here the theta, the way we have defined is what? It is the angle between the ground and the horizontal, okay. Y is the depth of flow perpendicular to the ground, okay. See the way we have defined this y is perpendicular to the ground. What is x? Well, x is the one dimensional flow or the direction, okay, in x direction. X is representing your direction in which the flow is one dimensional, okay, which is parallel to the ground, okay. X is the direction of flow which is parallel to the ground. V is the velocity of flowing water at the outlet, okay, and that what is the direction? It is parallel to ground again, okay. And what is L naught? L naught is the length of the ground which we are considering, okay. So, you see that we are considering a length L0, okay. So, if you have a very large catchment, you can subdivide it into different small catchments or different flow lengths, okay, depending upon the need, all right. So, you would have certain flow depth and velocity coming out of this this portion, and then next you have another overland flow, all right. If you want to model that, then you will have an input coming from upstream, and then you want to calculate what is the flow depth and velocity outside of that, okay. So, we are not doing that, we are just taking one element of overland flow of length L naught, okay. All right. Now, what I would like to do is I will also look at the cross section of this overland flow or this control volume, what is happening if you look at it from the right hand side, okay. So, if you did that, let me see, actually this cross section would come here, okay. I do not have the space, so I am going to draw it here, okay. So, you have this like this, okay. If you are looking from the right hand side, just perpendicular to the direction of flow, okay. So, this is your ground level, this is your depth of flow y, okay. You have infiltration F going into the ground, you have I coming into your control volume, okay, and let us say that this is what, this is perpendicular to your first figure, all right. So, what we will do is we will take a unit length perpendicular to that. So, this is 1, okay. So, the width we are taking perpendicular to the board is unity, all right. Length is L0 and the width is unity, okay. So, with that what we will do is we will write the continuity equation, okay. All right. So, what we will do in this case is when we write the continuity equation, we will say that we are going to do that for steady state conditions, okay. What does that mean? That means that you have the rate of rainfall intensity is falling at a certain rate, infiltration is taking place at a constant rate after a very long time, right, and then you have the surface runoff taking place and sufficient time has elapsed so that the flow depth and the velocity are constant, okay. So, everything, this whole process is a steady state process, all right. So, when you write the continuity equation for a steady state process, again you apply the extensive property, intensive property, the left hand side is 0, on the right hand side you have two terms in the Reynolds transport theorem, all right. First term is the accumulation, because of the steady state nature there is no accumulation, all right, there is no increase of mass within the control volume, right. So, then your continuity equation will be double integral over the cross section or surface cross section beta rho dV plus beta rho v dot dA. Beta is 1, rho is it can cancel out or come out. So, all you have is v dot dA is equal to 0 and this we will say is 5.6.1. Okay. So, I am afraid I am going to have to stop at this point of time. So, all we have done is we have defined the schematic and the overall problem of calculating the flow depth and velocity for overland flow, okay, and we will come back and look at this continuity and momentum equation tomorrow.